We're now ready to finish our proof that the Goodstein function grows quickly. In a previous video, we reduced that to two claims. The first claim we promised to prove is that for each ordinal alpha, there is some n so that for every m greater than or equal to n, gamma m of m is greater than or equal to alpha. To prove this, we'll have to really dig into what happens with the gamma sequence. We'll make this argument out of a series of smaller arguments. First, we can find an n so that gamma 1 of n is greater than or equal to alpha. Remember this function b omega 2 of alpha that writes out alpha as a sum of terms and then replaces all the omegas with 2's. Before, we worried about the fact that it doesn't invert, that b2 omega of b omega 2 of alpha might not be equal to alpha. But when they're not equal, it's because b omega 2 of alpha is not in hereditary base 2, and so terms collapse into terms with higher exponents. But the higher exponents only make the terms bigger, so we at least have b2 omega of b omega 2 of alpha is greater than or equal to alpha. So we can take n to be b omega 2 of alpha, and then gamma 1 of n is just b2 omega of n, which is at least alpha. Second, if we take any m greater than or equal to the n from the first part, gamma 1 of m will be at least gamma 1 of n, which is at least alpha. So for any m greater than or equal to n, gamma 1 of m is greater than or equal to alpha. But we don't want gamma 1 of m to be at least alpha. We want gamma m of m to be at least alpha. So we need a way to make what happens at stage 1 relevant to what happens at a later stage. So now we have an argument 3. Suppose that n is any number, and gamma 1 of n is some ordinal beta. Then we claim that for every I less than or equal to g of n, for every I for which the Goodstein sequence starting with n is defined, gamma I of 2 times n is greater than beta plus gamma I of n. That sort of makes sense. Gamma 1 of n plus n, you could imagine, should be something like gamma 1 of n plus gamma 1 of n. And then you have this beta plus beta, and at every stage you subtract from one of the betas and leave the other beta alone. And that's kind of what happens, though the actual argument is a little more complicated. The proof is by induction on I. So we start with the base case where I is 1. N, written in hereditary base 2, is 2 to the something plus 2 to the something plus ... 2 to the something. And gamma 1 of n is going to be omega to the b2 omega of that first thing plus ... 2 times n is the same as increasing every exponent in n by 1. It's 2 to the c1 plus 1 plus ... And so gamma 1 of 2n replaces all those 2's with omegas, and the exponents become b2 omega of the exponent plus 1. Adding 1 to c1, well, that's at least as much as adding it outside the ordinal. b2 omega of c1 plus 1 is at least b2 omega of c1 plus 1, which is the same as omega to the b2 omega of c1 times omega plus ... because adding 1 in the exponent is multiplying by omega. But multiplying by omega is more than multiplying by 2, so that's greater than multiplying by 2, which is what adding gamma 1 to itself would do. For the inductive case, suppose that gamma I of 2n is greater than beta plus gamma I of n. We're going to use the lemma from the previous video about complexity. Beta is b2 omega of n, so in particular its complexity, tau of gamma 1 of n, is equal to 1. Tau of gamma I of n is less than I, so the sum has complexity at most I. Tau of beta plus gamma I of n is less than or equal to I. And now we have that lemma. Beta plus gamma I of n is less than gamma I of 2n, and its complexity is less than or equal to I, so gamma I plus 1 of 2n is greater than or equal to beta plus gamma I of n. Gamma I plus 1 of n is less than gamma I of n, so gamma I plus 1 of 2n is strictly greater than beta plus gamma I plus 1 of n, which completes the inductive step. So that completes part 3. For every I, gamma I of 2n is greater than beta plus gamma I of n. Next, we need to prove that some specific values are big enough. Notice gamma 4 of 4 is greater than or equal to omega. We can verify that by hand. The Goodstein sequence starting with 4 is 4, 26, 41, 60. 60 is more than 5. 60 is 5 squared plus 5 squared plus 5 plus 5. So gamma 4 of 4 is b5 omega of 60, which is omega squared times 2 plus omega times 2, which is bigger than omega. Next, for any m greater than or equal to 4, gamma m of m is greater than or equal to omega. By induction, the base case is what we just did, and if gamma m of m is greater than or equal to omega, gamma m of m plus 1 is greater than gamma m of m, which is greater than or equal to omega. Tau of omega is 1, so by that lemma on complexity from the last video, gamma m plus 1 of m plus 1 is greater than or equal to omega. Now we're ready to actually prove the claim. We have some ordinal alpha. We'll round alpha up to the nearest multiple of omega. That is, if alpha is some ordinal alpha prime plus a finite k, we replace it with alpha plus omega. So, without loss of generality, we assume alpha has no finite part. Take n big enough that gamma 1 of n is greater than or equal to alpha, n is greater than or equal to 4, and n is greater than or equal to tau of alpha, and consider any m greater than or equal to n. We know that gamma m of 2m is greater than gamma 1 of m plus gamma m of m, which is greater than or equal to alpha plus omega. Gamma m of 2m is greater than the ordinal alpha plus m plus 1, and tau of alpha plus m plus 1 is less than or equal to m plus 1. That's why we needed alpha to not have a finite term, so the complexities wouldn't combine. By that lemma about complexity, gamma m plus 1 of 2m is greater than or equal to alpha plus m plus 1, and we can iterate this argument. At each step, we're going to subtract 1 from that m plus 1 term. Gamma m plus 1 of 2m is greater than alpha plus m. Tau of alpha plus m is less than or equal to m, but certainly less than or equal to m plus 2. So gamma of m plus 2 of 2m is greater than or equal to alpha plus m. And if we continue this, gamma 2m of 2m is greater than or equal to alpha plus 1, and certainly greater than alpha. Why did we do alpha plus 1? Because 2m is even, and we want to consider the odd number. Gamma 2m of 2m plus 1 is at least gamma 2m of 2m, which is greater than alpha. So gamma 2m plus 1 of 2m plus 1 is greater than or equal to alpha. So for any m that is greater than or equal to 2n, to 2 times the maximum of b omega 2 of alpha, 4 and tau of alpha, gamma m of m is greater than or equal to alpha. On to the second claim. If gamma I of n is greater than or equal to alpha, and tau of alpha is less than or equal to I, then gamma I plus 1 of n is greater than or equal to alpha bracket I. First, we want to show that for any alpha and any I, tau of alpha bracket I is less than or equal to the maximum of tau of alpha and I. We show this by induction on alpha. We write alpha in that form delta plus omega to the beta, where omega to the beta is the last term. If beta is 0, then alpha bracket I is delta. Tau of alpha bracket I is just tau of delta, which is at most tau of alpha. If beta is greater than 0, then alpha bracket I is delta plus omega to the beta bracket I times I. So tau of alpha bracket I is the maximum of tau of delta, tau of beta bracket I, which is the maximum of tau of beta and I again. But that's at most tau of alpha or I. Now we can prove the claim. Once again, we're going to use that lemma about how the gamma sequence interacts with tau. If gamma I of n is greater than or equal to alpha, and tau of alpha is less than or equal to I, then alpha bracket I is less than alpha, so less than gamma I of n. Tau of alpha bracket I is less than or equal to I, so less than I plus 1, so gamma I plus 1 of n is greater than or equal to alpha bracket I. That completes the claim, and with the argument we gave a couple videos ago, that's the complete proof. For every alpha less than epsilon 0, there's an n, so that for all m greater than or equal to n, g of m is bigger than h alpha of m. The Goodstein function grows faster than every fast-growing function h alpha for any ordinal alpha below epsilon 0.